we are highly interested in this particular quantity. The derivative of, or the change in error with respect to the change in W, where W is some weight. Could be one of those elements of M, could be one of those elements of B. It's one of those parameters in the whole darn model, right? Why are we interested in this derivative? Because this derivative answers the question, if I change that one arbitrary weight, how does that affect my error? If this quantity is positive, that means if I make that W a little bigger, that'll make my error bigger. But I don't want my error to be bigger. So if this quantity is positive, that means I should make my W a little smaller so that my error will be a little smaller, so that my model is closer to fitting the data. Therefore, this quantity right here is basically the answer for which direction is downhill and how do I improve the parameters of my model. Okay? And I know this should be very boring and redundant to you because this is what the whole semester was largely about. That and what can we do with this? So, given that we want this quantity, how can we compute it? Well, it's going to be the partial of W. It's going to be the partial derivative of that, right? Of that sum squared error thing, which is, where'd that line come from? I don't know what that line is. Just pretend it's not there. Partial derivative of sum sub I of y sub I minus, and I'm going to replace y hat with f of m2 times f of m1 times x plus b sub 1 plus b sub 2 point. Let's see, I'll line up my parentheses. Paste that down here. Dang it, I lost a minus sign right there where my mouse hand is. Why'd that go away? Oh, that's because that's not a real minus sign. That's one of those funky office characters. Wink. There. So, this derivative is equal to the partial derivative of that thing with respect to partial derivative of W, right? Why are they equal? Because this thing is E, right? It says right there, E is equal to that. All I did is replace the y hat with the equation for y hat. So you can see what I'm doing here, right? Nobody's lost. That's for some reason the step that people just get the most boggled by. What am I doing at the very start? And if you get the start right, the rest is just math. Do a bunch of math and then you get what comes out. Backpropagation, right? Where did backpropagation come from? Somebody did this math. And when they did this math, they arrived at, oh, if we do this, then it updates the equation. And how do you get that out of math? Well, you code it up. Okay, so yeah. How then do we differentiate this? Here's what we do. I'm going to go into the brief version now because I think I don't need to repeat this a lot. But we're going to differentiate this. What are we summing over here with this I? This is every single pattern in your training data, right? Because y sub I is the label for training pattern I, and this x sub I, pretend there's a little I right there, is the features for training pattern I. And yes, I know I'm using italic letters here because I didn't want to take the time to type math boldface for all of them, but these letters could be boldified. It works just fine with vector math. Okay. Very important to understand that I is over every training pattern. If we actually compute true backprop, true gradient descent, we differentiate this for every single pattern in our training data. And the result is going to be summed over every single pattern in our training data. right? But if we, why did I delete all that? If we decide to do stochastic gradient descent, then we can basically omit the sum and just say it's equal to this thing, right? Why can we drop the sum? Because we're just going to do it one pattern at a time. Turns out that's a great thing to do because when you take the steps one pattern at a time, you're doing way less math per step, and it ends up being a lot faster, and in the long run it works pretty well anyway. Same principle as Wikipedia. Lots of tiny edits add up to about the same thing as you'd get if you had a great big meeting and everybody hashed out in the meeting what to do, and then you went out of the meeting and made the edit. But having a meeting with everyone on planet Earth would take too darn long. So there you go. Okay. The next step is going to be, I don't like that bar there. I'm going to fix it. Why is my font in so many weird sizes? I don't know. There, fix that. So I can delete that, cut that. Sorry, I'm OCD. There we go. That's going to be equal to the partial derivative of, now this y sub I, does changing your w affect your label? This is in your training data, right? If you muck with the parameters of your model, does your training data change? The answer is no. Therefore, I can simply drop that y sub I, and I can also pull that minus sign out in front just because I want to. And I can now just put this right there.
Did we lose the square?
Yeah, what happened to that square?
So now there's a negative sign in front, and that means that it's that whole quantity there before we apply the minus. So if the whole quantity is negative, then that means the EDW is negative. Which way do we update? We update.
Okay, so remember what we're calculating. Assuming I made no other math mistakes that you guys haven't yet caught, and I think I haven't. What we're calculating is the partial derivative of the error function with respect to the weight. This answers the question, if I change that weight positively, how does it positively affect my error? And because error is bad, we're going to want to subtract this thing. That thing is equal to this whole thing. So we're going to want to subtract this whole thing. And because there's a minus there, we could just say we actually want to add this thing. But let's not do that yet. Let's do that at the very end, just so we're not forgetting things or getting confused. So if there's a minus there, it's because we're remembering that we're going to subtract the thing. By the time we actually get down to implementing it, we're just going to drop the two minuses and we're going to add the positive equation. Does that make sense? Yeah. Let me just say it really slowly, just make sure we got it. This is how much the error changes when you change the weight, meaning if the weight is increased, the error increases. That's why we want to subtract this thing. All these equal signs are true equal signs. That means that ratio has this minus in it. And this whole thing is what we want to subtract. Because we're subtracting a negative, we will end up adding it without that negative. I don't know if that was any slower or better, but at least I repeated myself. Okay, and there's supposed to be a, God, I'm having parenthesis troubles today. That parenthesis needs to be right here. It's a terrible parenthesis. Okay, well, yeah. But anyway, I could retype it all, but I'm just not in the mood. So now, how do we start differentiating this?
I guess should
Yeah.
the y still be in there because it was part of the square?
Okay. I am getting ahead of myself and I'm making mistakes. I better stop all of this. Let's put this 2 up there. And now, let's do it the right thing. That is going to be the partial derivative of, tell me I have it down here. I don't. Okay. Y sub I minus f of m sub 2 of f of m sub 1 x plus b sub 1 plus b sub 2 squared. Dang it, I lost my minus sign because I have to copy this minus sign, paste it on top of the pretty minus sign, LaTeXify that. Okay. If we back up, here's our equation. All I have done so far is dropped the summation. And now this is correct, right? Okay. Assuming that's the case, the next thing I'm going to do is I'm going to drop that y sub I and pull that minus sign out in front. And the reason I can do that is, well, what just happened? Nope, I can't not do that yet. That's where I got confused last time. How does one take the partial derivative of something squared? The chain rule. And what does the chain rule say? It's the derivative of the whole thing multiplied by the derivative of the inside. So the derivative of something squared is you pull down that 2. So this is going to be equal to 2 times, where'd my equation go? Stop deleting my equations. Equals 2 times all of that times the partial derivative of y sub I minus f of m sub 2 times f of m sub 1 times x plus b sub 1 plus b sub 2. Zoom out just a little bit, scoot over here. Okay. I really should not have expanded this thing prematurely because in so doing I made this equation look horrible and nasty and very scary. Do you see that this whole thing just is y minus y hat from here to right there? Okay. And then we're multiplying by the partial derivative of y minus y hat without the square here. So all we accomplished was we got rid of that 2. And now what we're going to do is we're going to keep pushing that partial derivative off this way until it's gone. We're going to get rid of, and there's that minus that disappeared again because I am having the darndest time with those minuses. I apologize. I'm going to drop that y sub I, How do we take the partial derivative of an activation function? You just look it up. You multiply by the f prime of that, right? The derivative of the activation function of the input. See how this is what feeds input as input into the layer? Then we multiply by the derivative of the inside, as the chain rule says. And then we're going to peel it off one layer at a time. Multiply by the linear weights, multiply by the derivative of the activation function, multiply by the weights, multiply by the derivative of the activation function. Finally, when we're done, we'll end up multiplying by the input, and that whole thing is where backpropagation comes from. Okay, as you can see, I just got tired of doing math and started waving my hands. How do you feel about the big picture? Do you want me to go through the painstakingly slow math and do it for you all the way? Or are we good? Do you want me to actually do it step by step? Because I can. Maybe I can. I'm making a lot of mistakes today. Okay, I'm feeling bad about how I'm ending this. I was just asked to do this. I can do it. I did all the parts where people really screw up. Nobody really seems to screw up after they get to this point, except sometimes they do when they're differentiating the activation function. Don't forget to multiply by the derivative of the inside. If you do that, then it tends to work out.